Believe it or not, the very first commercially available televisions were largely mechanical, displaying images using James Logie Baird's process we discussed last episode, of a neon bulb in a spinning Nipkow disc. His model, the Televisor, was the most popular, but while completely revolutionary, at this time the TV was yet to be a commercial success, with much broadcasting at the time being purely experimental. And due to the small size of the image, it wasn't exactly a relaxing sit-back-on-the-couch experience. It took a new technology breakthrough to see the TV explode in popularity and with a great increase in image quality. This technology had the wonderfully science fiction name of the cathode ray tube, and the process of how it works honestly lives up to the sci-fi potential of its name. The precursor to the cathode ray tube was something called the Crookes Tube, unsurprisingly invented by an English physicist with the last name Crookes in around 1869. A Crookes tube involved a glass bulb that contained a partial vacuum, which means that the majority of the air particles have been removed. Within that bulb are placed two electrodes, one positively charged, the anode, and one negatively charged, the cathode. And when enough voltage is sent through, the cathode fires electrons in a perfectly straight line towards the anode. Now, because this is happening within a partial vacuum, there is very few other particles for the electron to collide with. So it not only moves in a perfectly straight line, it also moves at an incredible speed, so that most of them will fly straight past the anode, striking the other end of the glass bulb. When they strike the atoms in the glass, they cause such a spike in energy levels that it causes a visible glow. And researchers discovered that if they painted the inside wall of the glass with a phosphor, a chemical that emits light when exposed to radiant energy, that the glow would become even brighter. They also discovered that not only would the electrons travel in a perfectly straight line, but when a magnetic field was placed nearby, the path of the electrons could be caused to bend, using principles we've discussed in previous episodes. And right here we have all the basic components needed to create a bright television display with much greater clarity than Baird's Televisor. The beam of electrons came to be known as a cathode ray, and so a variation on the Crookes tube came to be known as the cathode ray tube. And it turns out that when you build a big enough one, the back wall of the glass bulb is a great television screen. But how did it create a television image? Well, it built it line upon line, just the same as the Nipkow disc approach. So let's say we want to start with just showing the top left dot of our transmitted image. Our cathode will receive a charge that varies in accordance with the brightness of the image being transmitted. It fires an electron beam of corresponding strength, and magnetic fields are used to direct that beam towards the top left. It strikes the phosphor-painted inner wall of the back wall of the cathode ray tube, which is also the screen, and we see a bright dot in the top left of the screen, which brightens or dims in accordance with the image being transmitted. Now, just like how the Nipkow disc spun fast enough to create the illusion of a complete continuous image, the magnetic fields can vary to move that electron beam from left to right, then down a row, then left to right, then down a row, continuing like this onwards to the bottom of the screen, before returning to the top and repeating. Only it does this so fast that to our eye, it appears to be a complete, bright, moving image. Incredible. And this technology reigned supreme for TVs and display monitors of all kinds until the explosion of consumer flat screens using plasma and LCD technology in the late 1990s. The first man to create a working cathode ray tube television, which came to be commonly known as a CRT television, was the Japanese engineer Kenjiro Takayanagi, which he publicly demonstrated for the first time on Christmas Day 1926. Though at this point he was only displaying a still image and had not yet developed the step of using magnetic fields to move the electron beam. From this point onwards, the global competition was fierce to invent, patent, and make commercially viable the best TV technology possible, with progress being significantly halted by World War II. But once the war had run its course, the TV exploded both in its advancements in quality and its use. In 1946, at the conclusion of the war, 0.5% of US households had a television, but by 1962 that had skyrocketed to 90%. In Britain, by 1968 there were 15.1 million households with a television, a number that was only 15,000 at the end of the war. There is so much more to explore in this process. The invention of colour, 3D displays, how the human eye works, the development of new camera sensors and how flat panel displays work, and hopefully one day we'll have the chance to get into that. But for now, we've uncovered the foundations of the process that defined all that followed. And now we're going to look to the next big leap, which is also the final step in our journey of exploring the process of how we communicate. And this final step is the one thing that brings together everything we've covered so far. Language, writing, books, using electronic signals to send audio and images, and displays and speakers to hear and watch with. It could be the biggest and most complex part of the process, and is the key that makes so much of our modern world possible: the internet.